Welcome back to Ashok's Army. This is Lab 5, and we're going to be measuring spherical aberration in a system using a Hartmann mask to simulate different rays propagating through our system at marginal focus and paraxial focus. This will allow us to create transverse and longitudinal ray fan plots that can then be compared to theoretical plots that we obtained from Zmax simulation. We're also going to be exploring how shape factor affects spherical aberration. So spherical aberration occurs from the curvature of a lens or a mirror, where rays falling on the outer edges of the optic are brought to a focus at different points than those falling in the middle due to the nature of its spherical shape. Now, the marginal focus is, of course, where the outermost rays, those marginal rays, intersect the paraxial image plane. And the paraxial focus being where the middle ray or chief ray intersects that paraxial focus plane. Now, we live in a 3D world, and so ideally we want all of them to focus at the image plane, perpendicular to the optical axis at a single point, which would be the reference point. Longitudinal spherical aberration is the distance between this image plane and where the rays cross the axis. Transverse spherical aberration is the distance from the optical axis at the paraxial focal point. Defocus simply indicates that the actual image plane is displaced from the paraxial image plane, which causes blurriness, similar to how spherical aberration will cause blurriness in your images. This is worth noting because spherical aberration and defocus are the only terms independent of field height and only depend on pupil coordinates. Thus, defocus can balance out spherical aberration by shifting the image plane from its paraxial focus.
So tilt, on the other hand, depends on field height linearly, and ray fans are independent of pupil. A tilt around x-axis has no effect on the sagittal ray fan and no effect on zero field.
To begin this lab, we have this L-shaped rail system. We have our laser, pentaprism, Hartmann, lens, and then our microscope, where our NA is 0.4, which is much larger than previous labs.
So the NA of your microscope objective really determines how much light you're going to be collecting from this Hartmann mask. So we found that 0.4 was actually the minimum that you want in order to collect the most light.
So now we're going to be creating transverse ray fan plots and longitudinal ray fan plots. This Hartmann mask is used to simulate the rays that would come from a beam that would propagate through this lens, and so that represents the different beams. On the outer edge right there, say the leftmost hole, that's going to represent the marginal ray. And so by seeing where the ray falls on the crosshair, we can find our marginal focus. That's going to be used as a reference when we scan the pentaprism through the rest of the holes and then adjust the microscope so that the spot lines up onto that marginal focus position, and this would create the transverse ray fan plot.
As you see, we started 1 in the middle and then it just moves left, so to 2, to 3, 4, 5, 6, 7, all the way to the right, and then all the way back to the left with 8 and 9.
Then, instead of using the leftmost hole as a reference, we're going to repeat this experiment by using the center hole as a reference, because that's going to represent our chief ray propagating through the middle of the system. So here is our paraxial focus. And so then we will repeat the same experiment, adjusting the pentaprism through the different holes and then adjusting the microscope so that it lines up on the paraxial focus, and that would be our longitudinal ray fan plot. This was done with the plano side of the lens facing the prism. That's going to create the most spherical aberration because we have a collimated beam coming in, and now we're going to flip it around where there's less spherical aberration with the curved side facing the beam.
Shape factor is the ratio of surface curvatures that describes the shape of the lens, and you can see from here it goes from -1 to 1, where your plano sides define the boundaries. Now with the curved side towards the source, so less spherical aberration, you can see it stays within these black bars of our little screen holder here. So much less spherical aberration in this configuration. And now to minimize spherical aberration with shape factor, you got to use this equation, and in our case it turns out to be about 0.7. Okay, so after modeling our lens in Zmax with the plano side towards the source of our collimated light, you can see that our ray fan plots show a 0.5 value for our top peak in our ray fan plot. And then in our measured data, we also get a similar value. So they both follow the same shape, and get similar data.
Now if we look at our longitudinal ray fan plot, it's a similar shape between these two graphs. So in Zmax with it modeled, Zmax only shows us the part of the graph that's coming from the x-axis, and that's kind of what we have here with this similar shape. We have more data points where the shape continues, but what's promising about this is that we get a similar value of our measured value of 0.6, and around here it's about 0.7 when it crosses the y-axis.
So we're looking at the transverse aberration again, but now with the lens flipped, so the radius side is up towards the source. So you can see the aberration is much less now from the Zmax file. And looking at our data over here that we acquired in lab, the aberration is much smaller. So in the previous setup, this was up to 0.7, now it's at 0.06. So the reason it has this shape is just almost noise. It's really small values.
All right, then with our lens flipped around again, this is our longitudinal ray fan plot, and it looks a little different than our experimental, but that's just because this is only graphing part of it, whereas we graph the full thing. So as we can see on the left side of the y-axis, it sort of follows a general trend where it's moving in this direction.
So in this setup, error can come from the misalignment or the inaccuracy of the pentaprism. When we move this pentaprism up and down to scan across the Hartman slide, these rays weren't actually going parallel with the rail. They were going off in some other direction due to some inaccuracy with the pentaprism or rotation of the pentaprism.
That error that Caleb just explained to you, we have wavefront error and ray fan error. So wavefront error is the optical path difference between the reference wavefront and the detected wavefront phase measured at the exit pupil plane. The ray fan error, on the other hand, is a singular object-to-image mapping whose path is perpendicular to the corresponding wavefront. Thus, the ray errors refer to displacements of a ray intersection with the image plane from a reference point, which is where the chief ray intersects the image plane. Ideally, the marginal rays would also intersect the chief ray, but they don't when there's error caused by aberrations. This can be in the transverse direction, which is the EX, EY plots that you saw, or along the optical axis, which would be the longitudinal ray error, EZ.